Greetings! Welcome to Electronic Circuits 1. I am Razavi and this is lecture number 18. Today we will look at the early effect again and try to see how it impacts the transistor model, both large signal and small signal. And then that will lead us to the complete small signal model of the transistor. Following that, we will look at the PNP transistors, another type of transistors. But before we go there, let's take a look at what we covered last time. Here's a quick review of lecture number 17. So we said that when we have biased abipolar transistors and there's no signal, we have a certain current in the collector, we also have a certain base emitter voltage. Now when the signal comes in and the signal is small, it produces a perturbation around the operating point. For example, the collector current might be at 1 milliamp, and as a result of the microphone signal, it just goes up and down by a few tens of microamps. In that case, we have small signal operation, and as far as the transistor's reaction or response to the microphone signal is concerned, we can use a small signal model. The small signal model tells us what happens on top of the bias conditions. And for that, we saw that we can arrive at the simple model consisting of R pi, which represents the base current that flows as a result of the signal. Or we can think of it as the changes in the base current as a result of the signal. Meaning that there is a base current, the bias base current, and then it goes up and down because the signal is coming in. And similarly, we have GM V pi being the small signal base emitter voltage that represents the changes in the collector current. So this should not be confused with the bias current that is necessary to produce a certain GM, certain good condition, amplifying condition for the transistors. So we also saw that GM is simply calculated if we know the collector bias current and the thermal voltage, 26 millivolts, and R pi, this resistance happens to be beta over GM. So once we have GM, we also have beta, we also have R pi. Okay, so what this tells us is that in analysis and design of circuits, we really have two different tasks. In task number one, we have to understand the bias conditions of the transistors when there is no signal. How much current do we have? How much base emitter voltage we have? How much collector emitter voltage do we have, etc. So those are the bias conditions to make sure that the transistor is healthy, meaning that it is in the forward active region and it has a reasonable amount of current, a reasonable amount of transconductance, etc. Now, we come along after we analyze the bias conditions and we go to the signal conditions. In a sense, we are using superposition. So we forget about the bias conditions now, we just look at what happens as a signal comes in. In this case, we can use a small signal model. That allows us to separate these two tasks and attack them independently. So that's a simplification in the analysis and design. All right, we also talked about the early effect in bipolar transistors. We saw that if we take a bipolar transistor with a constant base emitter voltage and change its collector emitter voltage, the collector current is not quite constant. It has a small slope to it. And we saw that that's because the depletion region in the collector base junction tends to protrude farther into the base, which means the base width is reduced when the collector voltage goes up and the current increases. And we saw that a very simple model to represent this increase is just a linear factor that is multiplied by our good old exponential. So we just say VCE, and then we have to get the units right, so we place some voltage here, which is called the early voltage. So that is, in a sense, the large signal model of the bipolar transistors. All right, so today we would like to start from here and then eventually arrive at the small signal model including the early effect. We will see that it's not just R pi and GMV pi, but there must be something else to account for early effect. So we have to figure that out. And that wraps this up, and then we go to another type of bipolar transistor, which we call the PNP transistor. Fortunately, that's not that extensive or that hard because there are great similarities between the two, so we can quickly go through that as well. All right, now before we start, I would like to just point out a confusion that often people have in regards to a large signal model and small signal model. So in correct view of large signal and small signal models. Sometimes when I give quizzes to my incoming students, I ask this question: what is the difference between the large signal model or the small signal model? And this is what they say. Large signal model is for DC, small signal model is for AC. Okay, that is incorrect. The source of this confusion is that, yes, we do use the large signal model for DC calculations, for bias calculations, but it doesn't mean that it's always just bias. The large signal model is a general model that allows us to analyze the circuit when we have not necessarily small swings, small changes in the signals that are coming in. So the signal going to the base emitter might be 100 millivolts, not much less than 26 millivolts. So that's the actual definition of the large signal model, a model that allows us to analyze arbitrary conditions applied to the transistor, of course provided that we are in the forward active region, not just DC. Also, the small signal model doesn't mean that it's only AC or it's always AC. If we have a signal, an AC signal, but it's too large, then this model fails. We have to go back to the large signal model. So this is incorrect. Remember that the large signal model just deals with arbitrarily signal levels, whereas the small signal model assumes small perturbations in the bias conditions. So that's something to remember. Okay, now let's go to early effect and see what we have to do about the small signal model of the transistors. All right, so we said that here's the situation. We have connected a variable voltage between the collector and the emitters and a constant voltage between base and emitters. And when we examine the collector current as a function of this VCE, we see that the current is not quite constant and it has some variation. So this is what ideally this is what we would like to have, but in practice this is what we see. All right, and the model that we just mentioned for this was the large signal model was IC is equal to IS x pub VBE over VT, and then 1 plus VCE over VA as a simple approximation of this behavior. Okay, so that's what we have. And now what we need to understand is how this translates to how this affects our small signal model. Okay, so now we have to have a more rigorous and methodical approach to calculating the small signal model of a device. What we did in the past was, well, we have a circuit for bias calculations, then we have a circuit for the signal calculation, and these are separated, and we came up with the small signal model. But let's try to be more precise so that in any situation for any device whose large signal model is given, we can easily find the small signal model. Always remembering that there is a linearization involved. We have some sort of nonlinear characteristic, and we're looking for a small portion of that characteristic, and that portion is approximated by a straight line. Okay, so here's our what I call official method of small signal model derivation. All right, so here's what we will do. In step number 1, assume the transistor is biased at a certain operating point. Okay, so remember that if we don't bias the transistor, if the collector current is 0 and we bring a signal to it, it's dead, it doesn't do anything. So we always have to bias the transistor to provide the right GM, etc., before we can apply a signal. So the transistor is ready to receive a small signal. Okay, step number 2. Apply a voltage change between two terminals so we take the voltage between two of the terminals and change it by some amount. For example, this one or this one. And measure the resulting current changes. Okay, so we apply a voltage change between two terminals, for example these two, while other voltages are fixed, and then we go around and see what this voltage change has caused. Has it changed a current here, a current here, a current here? Any current that has changed now needs to be modeled. So step number 3, model the changes, the current changes by proper electric devices. The candidates for these electric devices would be a voltage-dependent current source. Remember GMV pi? That's a voltage-dependent current source. Or resistors, like RPi itself. That was a resistor, just happened to be a resistor because it had a current in proportion to the voltage on it. So we call it the resistor. So those are candidates, and in most cases that's what we need. Okay, so with these steps, we can exactly find the small signal model of the transistor. So let's go ahead and apply these while we have early effect inside the device. Okay, so let's start by GM. That's the most important aspect of the transistor. And we know that it's defined as dIC over dVBE. So it means that the transistor is biased. It already has a certain current, for example, 1 milliamp. And now we go and change the base emitter voltage by some amount, some small amount, delta VBE, and we would like to see how much the collector current changes by. That is emulating the case of a signal coming in. If a signal comes to the base emitter voltage, it wants to change it by a small amount, and as a result the collector current changes, and that's why we need to measure GM. Okay, so now we have to use the new equation for IC, all of this. So that's not that big of a deal. The derivative of this is still just the derivative of this exponential multiplied by all of these things. So it's just IS over VT exp of VBE over VT, and then 1 plus VCE over VA. Okay, so can I simplify this the way I did before for GM? Well, do we see any familiar term here? You can see that IS exp of VB over VT times 1 plus VC over VA, that is the bias current, the collector current, right? So we say this is IC over VT. So fortunately, the GM itself hasn't changed, even though we have early effect, so long as we remember that the collector current calculated in the GM equation is the current obtained using early effect, right? So this IC is this entire expression, not just IS exp of VBE over VT. So that's all we need to remember. In other words, when we are calculating the bias conditions of the device, we have to remember that it still has early effect. So for bias conditions, we have to use this equation, right? All of it. And then we find an IC, we take that IC, divide by VT, we have GM, we're good. Okay, so that was easy. How about R pi? Does R pi change? Well, we remember that what is true is IB is always IC over beta, regardless of what's happening. In other words, the early effect does not alter this relationship between the base current and the collector current. So that means that if there is a change in the collector current, it just gets divided by beta and appears as the base current. So that means that we still have R pi is equal to beta over GM. Right? Because the collector current has changed by GM V pi. And that GM V pi gets divided by beta to give us the base current change. GM V pi divided by beta is the current, so the resistance equivalent to that will be beta over GM. So this doesn't change either. Okay, good. So far we don't have any serious problem with the small signal model. So if we go back to the model that we had here, we see that these two haven't changed. The only thing we have to remember is that this IC, the bias value, has to be calculated using this entire equation here, not just IS exp of VBE over VT. All right, so far so good. Now the question is, can I just write the model like this? So is this model correct? I have R pi, between base and emitter, and I call the small signal voltage V pi. Then this is GM V pi between collector and emitter. So does this reflect everything that's happening in the bipolar transistor now that we have included early effect? So we have to think about that for a second and ask ourselves, is there some other mechanism that this model does not include? Well, what we are saying is that if the collector-emitter voltage changes, the collector current changes. But we don't have that here. Here, this is the collector-emitter voltage. If this voltage changes, we don't see any change in the current. The current is always GMV pi. So something is missing, and we have to see how we can do that. So for that, we go to our procedure. The procedure said, apply a voltage change between two terminals and measure the resulting current changes everywhere. What we have done in arriving at these was to change this base emitter voltage, right? This is what we did earlier. The base emitter voltage is changed. The collector current changes by GM times that change. Then that's the current source that represents that. We divide that by beta. We got that for the base. That's all. But one test that we have not run yet according to this procedure is to apply a collector emitter voltage change and see what happens. So let's go ahead and do that. So in the next step, so the answer is no, this model is not correct. So let me write that here. So we say inclusion of early effect. Okay, so I will follow this procedure. I will draw the transistor here, assuming that it has certain bias. So I have a certain base emitter voltage. And now I change the collector emitter voltage. So we change the collector emitter voltage, and we would like to see what happens to these currents, IC and IB. And IE as well, but we usually assume IC is approximately equal to IE, so that's not a big deal. Okay, well, let's suppose that the collector emitter voltage makes this change. It starts from VCE and it goes to VCE plus delta V, a small change. So what we are asking is, when this voltage changes by some small amount, it starts from a bias value, let's say 1 volt, and changes by a small amount, let's say 10 millivolts, 5 millivolts. The question is, what happens to the collector current? It probably changes, so if it changes, that has to be modeled somehow, not like this. Okay, well, it shouldn't be that hard to find the change in the collector current if we have this. Then we just go back here and assume that VCE is now equal to VCE plus delta V. So we can say IC plus delta IC is equal to, because I know that IC is no longer the old IC. There's a new IC, so that new IC is called IC plus delta IC. That would be IS XPOV VBE over VT. So we just we write this as VCE plus delta V. So that would be 1 plus VCE over VA plus IS exp of VBE over VT times delta V over VA. I hope it's easy to follow that. What I did is, in here, I replaced VCE with VCE plus delta V. And I assumed that there is a change in the collector emitter voltage, therefore there is a change in the collector current. Maybe, maybe not. If not, then eventually it should be 0, right? So, and then I just expanded this and I got this. Okay, so what can we recognize here? Well, this is the original IC, so that's not surprising, right? And this is delta IC. So then we can just say delta IC is equal to IS exp of VBE over VA times delta V over VT here divided by VA. Now we didn't have to do it this way. We could also simply take the derivative. We could take the derivative of IC with respect to VCE, and we would end up with the same equation. Delta IC over delta V would be all of this. Okay, so this is what we have observed. We observed that if this collector emitter voltage changes, this current changes. And the relation between the two is linear. Right? You can see delta IC is linearly proportional to delta V, so long as base emitter voltage is constant. And it is constant because that's what happens in our test. So for a given base emitter voltage, if we increment the collector emitter voltage by delta V, then the current in the collector increments by this much. So now the question is, can I go back to that small signal model and try to reflect this phenomenon in that model? So let's draw the small signal model again. Here's what we have: R pi, V pi, GM V pi, and this is the emitter, this is the base, this is the collector. And what we observe is that if the collector emitter voltage changes, there's a current drawn. And the relationship between the current, the increase in the current and the increase in the voltage is linear. So imagine, again, you put all of this in a box. And what you see is that when we increase this voltage by delta V, this current increases by some delta IC, and they are related by a linear term. So how do we model that box? How do we model this behavior? It's just a resistor. So as far as the changes are concerned, it's just a resistor. So we can place a resistor here. How much is the value of that resistor? Well, if this is the change in the current for this much change in the voltage, then the resistance would be inverse of this. So the resistance would be given by VA over IS exp of VBE over VT. Now, because we don't want to write this all of the time in this model, we will give this resistor a name, just the way we did this one. We will call this RO for output resistance. And this RO happens to have this value. So this is RO. So just the way GM was equal to IC over VT, R pi was beta over GM, RO is equal to VA, the early voltage, divided by this. Can we simplify this? Well, IS exp VB over VT, this is our original estimate of the collector current. Not the exact value, because the exact value has this factor. So we will make an approximation only for RO. We say for RO calculation, we say that this is approximately equal to the collector current, because this term hopefully is not much different from 1, meaning that this slope is not very sharp. So we will say RO is approximately equal to VA over IC. And that is the bias calculation. After we know how much bias current we have, we plug it in here, we find the output resistance. We find RO. This is the complete small signal model of the transistor, at least at low frequencies. All right, IC is the bias current, VA is the early voltage. The early voltage, as I said before, goes somewhere from a few volts to a few tens of volts, depending on the transistor that you buy. And IC, of course, is the value that we have, maybe a few milliamps. All right, so we have derived the small signal model of the bipolar transistor in its entirety. And that completes this section. Let me just see what else we need to cover here. Okay, so I'll just add another little note here. Let's try to plot IC as a function of VCE, like we did before. Okay, but this time we will be more courageous. So IC VCE. So we said, well, it's not quite straight, it's not quite flat, it's a little tilted. All right, but we will be courageous. We will let VCE come down more and more and more. We will let this voltage collapse. What happens as this voltage collapses? Okay, so let's say the base emitter voltage is 800 millivolts, a typical value. And let's say VCE starts at 1 volt. So around here, we are at 1 volt. Is the device in forward active region? Yes. The base emitter is forward biased, and the base collector junction is reverse biased, because we have 1 volt from here to here, we have 0.8 volts from here to here, so this point is 200 millivolts more positive than this point. So the device is in forward active region. Okay, now VCE comes down. VCE comes down to, for example, 800 millivolts. So this is 800 millivolts, this is 800 millivolts, collector and base junction has 0 voltage on it. That's still okay, not a big deal. But now we come down even more. So for example, this comes down to 500 millivolts. Now, if this is 500 and this is 800, the collector is less than the base, so the base collector is forward biased. And that's not what we would accept in forward active region. Now, if we keep doing this, what happens is that suddenly the collector current falls. And when VC goes to 0, it goes to 0. So, the point at which this sharp drop occurs is something we want to avoid. So our VCEs in any design, in the bias condition and with the signal coming in, must always be large enough that we don't get into this region. That region is very undesirable for bipolar transistors. So, in other words, we want to stay in the forward active region. We don't want to go here. This region, to distinguish it from forward active region, is called saturation. So we want to avoid the saturation region. Saturation needs to be avoided. So strictly speaking, saturation is avoided if the collector emitter voltage is equal to base emitter voltage or higher. In other words, this junction has 0 bias on it or a reverse bias on it. So if this VCE comes down to 0.8 and then starts going below 0.8, we enter saturation. All right? Okay, now this was for one base emitter voltage. If you have a different base emitter voltage, what happens? Well, we get a similar plot. So we have a bunch of plots that go like this. And those are for different base emitter voltages. This is a general IV set of characteristics for the bipolar transistors. All right, so to avoid saturation, we say VCE should be greater than 800 millivolts. Okay, so to avoid saturation. But in practice, actually, it doesn't have to be so strict. Think of it this way. Let's suppose that I keep the base emitter voltage at 800, but I reduce the collector voltage to 500. So now I have a forward bias from base to collector equal to 300 millivolts. Is that really bad? Well, we know that for typical designs, typical transistors, if a junction has only 300 millivolts of forward bias on it, its current is very small. Right? We have to get to 700, 800 millivolts before we have a reasonable current or a significant current. So even though we have a forward bias of 300 millivolts between the base and the collector, it's not detrimental to the transistor operation. And that's what we call soft saturation. So soft saturation is allowed so long as we are very careful and we do not let that go into deep saturation. So I will write that. Soft saturation is defined as VCE greater than, let me erase this, make some more room here. So VCE is greater than 0.5 volts and less than 0.8 volts. Okay, so that's still acceptable, even though we have a bit of forward bias across the base collector junction. So that's good to remember. All right, this completes our study of the bipolar transistor and the small signal model. We still don't know what the small signal model is good for because we haven't built actually any circuits yet, right? But don't worry, we'll get there and we'll see how useful it is when we have that. Instead of analyzing circuits using exponentials, we can analyze circuits using these simple models. Very well. Let me check my notes here and let's see. Okay, so let's go over an example just to get comfortable with these ideas. So let's go add a page here and we go to an example. It's just a numerical example to see how these come about. We will assume that we have a bipolar transistor and we are biasing it, and we would like to find the small signal model of that transistor. So here's a transistor that we have biased with two batteries. This battery is 800 millivolts. And the other battery I have chosen to be 1 volt. So that's 1 volt. And our objective is to find the small signal model of the device. All right? Okay, so the first thing to do is find the bias quantities, in particular the collector current. Well, is the device in forward active region? Yes, because the base emitter is forward biased and the base collector is reverse biased. So we're good. We can use the equations that we had before. So we say IC is equal to IS exp of VBE over VT times 1 plus VCE over VA. Now for this transistor, we are given some parameters. We are given an IS of 5 times 10 to the minus 16 amperes. Beta is 100, and the early voltage is 5 volts. So these are parameters that you would see if you look into the data sheet of the transistor. All right, so now we plug in IS, and VC equals 1 volt, VB equals 800 millivolts, VA equals 5 volts. And that will give us the following number. It comes out to be 13.8 milliamps. It's somewhat of a high current, but that's what we get, 13.8 milliamps. All right. Now, for the small signal model, we need GM, RPi, and RO, 3 parameters. So let's calculate those. So GM is equal to IC over VT. 13.8 milliamps divided by 26 millivolts. And that is equal to 0.53 Siemens, or sometimes we like to express it as this, 1 over 1.9 ohms. Either way is fine, but it's good to be comfortable with both representations. Okay, so then RPi is just beta over GM. So 100 times 1.9. So that's 1900 ohms. It's not that bad. What else? RO needs to be calculated. And we know that RO is equal to the early voltage divided by the bias current in the collector. Approximately, if you remember, this was not exactly the collector current, but that's okay. And from there, we can say it's 5 volts divided by 13.8 milliamps, and that comes out to be 362 ohms. So now we can construct our model because we have GM, RPi, and RO. So if we go back to the previous page, we see that the model is complete. We have RPi, we have GM, we have RO. So now for any circuit that uses this bipolar transistor under these bias conditions, we can use the small signal model. Very well. So let's go back to the other page and continue. Okay, that was the example that I wanted to show. Now, there's one little note that I wanted to share with you here. At this point, you may not appreciate why this is interesting or important, but we will see sometime later. And the note is this. So note GM, this value, times RO, this value. So GM RO is much greater than 1. You agree, right? This is about 1 over 2 ohms. This is 362 ohms. You divide, we get a factor of about 180. So it's much greater than 1. So GMRO is much greater than 1. GM, the transconductance, times RO, the resistance that we connect between collector and emitter in the small signal model, is much greater than 1. So some weeks from now, some lectures from now, we will see why this is interesting. Okay. So that covers this example. We are now ready to go to the PNP transistor. All right, the transistor that we have studied so far so extensively is called an NPN transistor. Because if you remember, it was constructed as an N piece of silicon connected to a P piece of silicon connected to an N plus piece of silicon. So one may naturally ask, can I swap these dopings and create a different type of transistor, which we will call the PNP transistor. So let's change the color, and we go to the PNP transistor. So the PNP transistor is simply like before, except that we have, for the collector, a p-type material, so it's doped with acceptors. For the base, we have an n-type material, and for the emitter, we have a p plus material. So everything is switched around. Okay, and this device is represented in circuits by the same symbol almost exactly, except that to make sure we don't confuse NPN, which is what we have studied before, with PNP, we change the direction of this arrow. So the arrow now goes this way. Okay, so you can think of it this way, that here the conventional current was going this way. Now here the conventional current is going that way. Either that or however you want to memorize it, but this is the symbol for the PNP transistors. Okay, so we want to bias this PNP transistor in the forward active region. So we have to forward bias the base emitter junction. This is the base, this is the emitter. How do we do that? We need to connect a battery, but which side of the battery goes where? Well, this side has to be more negative than this side to be forward biased. So I have to connect the battery like this. Negative here, positive here. All right, so that's where things may be a little confusing compared to the NPN case. Okay, we also need a battery between the collector and the emitter, like before. And what do? Well, the collector has to be more negative than the base to keep this junction reverse biased. So we also have to have a battery with this negative side over here and this positive side over here between the collector and the base. So it's very important to remember these differences with respect to the PNP device. Okay, how does the current flow here? Well, remember in the case of NPN, we said we have electrons starting from N plus and flowing to the base. Now here, as you might guess, we have a lot of holes going from P plus to N. So we have lots of holes going this way. And then we have a few electrons going this way. Just the opposite of what we learned in the NPN device. The holes start from the emitter, cross the base. Because the base is so thin, they all cross the collector. Most of them cross the collector. They reach the depletion region and shoot through the collector and are absorbed to the battery. So the current, the conventional current associated with positive charge is this way, right? Not the other way. So that's also a difference between the PNP device and the NPN device. So the current is going this way. That is IC. How about the base current? Well, we see that we have electrons going this way. So the conventional direction of current is that way. So the base current is coming out of the base. Again, different from the NPN device. And finally, the emitter current is also this way. So if I draw them here, the collector current is going this way, the base current is going this way, and the emitter current is going this way. Now, in some textbooks, you might see this differently. So IC might be pointing this way, but in our lectures, this is the convention that we will go with. Okay, very good. So the operation is similar to what we had before. We have an exponential dependence, we have early effect, everything else is the same as before, except that we just have to be careful with these polarities, these junctions, the batteries, the way they are connected, which one is reverse biased, which one is forward biased, and so on. So, let's see. Okay, so to just make sure that this is completely clear, we'll say forward active region for a PNP device is shown as follows. The base emitter voltage, the base emitter junction must be forward biased. The base emitter junction must be forward biased. So that means that the base voltage should be more negative than the emitter voltage. So we write like this. We say VEB must be greater than 0, meaning that the emitter has to be more positive than the base. The emitter has to be more positive than the base. And now, for the base collector junction, for it to be reverse biased, we need the collector to be more negative than the base. Or as we saw before, the collector must be more negative than the emitter. So VCE must be, okay, sorry, let me write that correctly. So we have VEC must be more negative than VEB. This also guarantees that the collector is at a lower potential than the base, and this junction remains reverse biased. We can even assume equals, as we have seen in the past. All right. So, now, because of these differences, PNP devices can be quite confusing. So I would like to make sure that this is clear in your mind as you go along. And we have various visual aids to help us keep track of all these voltages and currents. So here's the way we think about it. In electronics, typically we place the positive voltage on top of the page and then negative voltage on the bottom of the page. So here's a positive voltage, here's a negative voltage. That's the convention that we use. As a higher potential on top of the page, lower potential on the bottom of the page. Now if we have an NPN transistor, is an NPN transistor, and we want to connect it to some voltage. Maybe we connect it like this, right? This goes up here, this goes down here. Collector is higher than the emitter. And then maybe we have another voltage for the base, so that is VBE. As we saw before, no problem there. You can imagine that this comes from a battery here. So place the battery over here, and we're good. So that is a battery. Now, when we want to connect a PNP device to the same circuit, to the same environment, we have to be careful. For the PNP device, we know that the emitter has to be more positive than the base. The emitter has to be more positive than the base, because this junction has to be forward biased. So what we will do is we will draw this device upside down. So we will draw it like this, just for convenience, because we know that the emitter has to be connected to a positive voltage. So we connect this here, and then the collector, well, it has to be at a lower potential. So remember, here the collector is at the lower potential than the emitter. So the collector goes here. And then we have to bias the base. So maybe I can connect a battery like so. Plus, minus. So this type of visualization of these two devices is extremely helpful when especially we combine these two in the same circuit. We have some NPN devices, some PNP devices. We have one positive supply and one negative supply, or we have one battery connected to the positive supply and negative supply. So we want to make sure that we don't get confused. So emitter goes to the highest potential, then base is lower by this much, to keep this junction forward biased, and then the collector goes to the most negative potential. All right, so now when we draw it like this, we have to remember that this terminal, the upper terminal, is the emitter, is not the collector. And that is where a lot of people get confused. So just remember that. Okay, one quick note. So this is what I call a visualization of how these devices operate. So let's draw the NPN device, which is more familiar, in 3 regions of operation. So NPN device, plus minus. Plus minus means the collector is more positive than the base. Which region of operation are we in? We are in forward active region, so I'll just write active. Provided, of course, that the base emitter is also forward biased. So we're not drawing that here. That's given, we know for sure. We're just looking at base and collector for now. Okay, now what if the base and collector have the same voltage? So we draw this in our circuit like this, and I bring these two up next to each other to indicate that their voltage difference is 0. So 0 voltage difference between these two. So where are we? Now we are at the edge of active region and saturation. Remember what happens, right? If this voltage is equal to this voltage, then the base collector junction has 0 voltage on it, so it's right at the edge of forward bias and reverse bias. So we are at the edge of saturation, we'll say edge. Again, remembering that there's always forward bias for base emitter. I have not shown that, I'm just looking at the base collector. And finally, if we draw it like this, just for our own edification, and say positive here and negative here, meaning that the base is now higher than the collector, then we are in saturation. Remember that if the base is higher than the collector, then the base collector is forward biased and the device is in saturation. So we say we are in saturation. In all these 3 cases, the base emitter junction is forward biased. We have not shown that here, just for simplicity. Now let's repeat all of these for the PNP device. So again, as I said, in most cases, we draw the PNP device with the emitter on the top, just for convenience, no other reason. So let's do that, and let's not get confused. So how do I choose this voltage difference to ensure that we are in active region? The base collector junction must be reverse biased. For that to happen, the collector has to be lower than the base. So we have positive here, negative here. This is active, right? The collector has to be lower than the base. So VEC has to be less than VEB. All right. Then you can imagine the edge would be similar. So we have these two are at equal potential, so 0 difference. That would be at the edge. And if the collector is higher than the base, a collector is more positive than the base, then we are in saturation. So we have like so. So saturation, I wrote it on top, so I don't need to repeat it here. So that's in saturation. So it's very important that you master these visualizations of the 2 transistors. This is the best way to avoid confusion. Of course, you can always write these equations and see if they are valid or not. But before you write these equations, it's good to just have this feel about what the transistors are doing in each of these cases. And then, of course, you can write equations to confirm what you thought, what you guessed. All right, that is the PNP device. And A few words about the model of the transistor. The large signal model is the same as before. We just have to be careful. So let me try to do that here. I need to get my pen back and change the color to maybe brown. So I will just talk briefly about the large signal model. So large signal model of the PNP device. Okay, so let's assume that we have drawn the emitter again on top, just the way we do in the actual circuits. So we have a base emitter junction, and that has a diode in it, if you remember. So there's a diode, and that diode needs to be forward biased. So we have a diode like so. This is the base, this is the emitter. Then we have a voltage-dependent current source, which exponentially depends on the base emitter voltage. So that current has to be going this way. Because remember, current always flows from positive side to negative side. And we know that for a PNP device, the emitter is higher than the collector. So the current has to go down. And this would be IS exp of something over VT. What is that something? Is it VBE or VEB? Well, we know that this voltage here is VEB. It is VEB that's positive, right? And that's what has to go in here. So VEB. And this would be the collector terminal. If we want to include the early effect, we simply multiply this by 1 plus V, again EC over VA. Assuming that VA itself is a positive number. So it's VEC because again E is more positive than C. So that would be VEC, and VA is a positive number. So this is the model that we would use. And again, the source of confusion when students face the PNP device is that they automatically think the terminal that's on top is the collector. It's not true. The way we draw it is like this. If you don't like this, no problem. You just flip it over. Flip it over, the emitter will be on the bottom, the base and collector will be on top, except that these polarities still have to be there. All of these have to be there. VEB, not VBE, because the emitter base junction must be forward biased. So that's the large signal model that we have for the PNP device. Since our time is up, I will stop here, and I will see you next time.